Let's do a video on using LTspice to extract an EKV spice model from a BSIM level 49 parameters. Alright, I can put this in the description, but here's the paper about doing an EKV model, and then here's a more detailed description, although there's some things that aren't quite in there just yet. Alright, but here's the file. Here's the first file to find the specific current and KP. So if we go to LTspice and we just run this, right, I can plot eventually plot the drain current. And the thing is there's a lot of choices of bias voltages, and I'm trying to find the best one where we can extract things properly. Alright, so if you follow that paper, right, you want to plot the square root of the drain current. Okay, and that'll eventually. And so the slope of this line will ultimately give you gamma, and then gamma will also give you the slope of this line will give you the specific current, and also we can find KP from there, right? But you need the slope of this line, and to automatically generate the slope of that line, I had to kind of play a trick where I have two circuits that are identical, but one source voltage is lagging the other by 0.01, and so then I just subtract the square roots of these two currents and then divide by that difference, and that gives me the slope. So that's that function value. Then I can put that into a measure script and then calculate IS and KP, which then we just go to the spice error log, plot the step measures, and then we go to IS, and we see that there's a peak. And that's the one that I found that gives the best value for KP, so that's what we're going to use. So here it's 343 nanoamps, right, which is we'll save for later, and then KP is 255 micro. So now we have our specific current that then we want to simulate. Right now here I had to, again, we're going to be ended up using derivatives to find things, and so I had to trick it, but where I'm stepping the bias current though, and that'll show you something interesting. Right, I'm just going to get rid of some of these. And you can see that there's the VT all being extracted where it crosses 0. And although it changes, it doesn't actually change that much. And we find that if we, again, we got to go to the spice error log to plot everything, extracting VTO. So the correct specific current was around 172, and so the threshold VTO is 785.86 millivolts. But notice it's going from 720 to 850 over, a wide range of currents. So it's actually pretty stable. Gamma, same thing. We're zoomed in on it quite a bit, but it really doesn't change that much for values of specific current. All right, and then we can find V, same thing. But still, I choose it at the bias point at half the specific current. All right. So once you have those two, all right, and then these are all the files are in the Google Doc, right, that can be downloaded, right. Then we have to find Lambda, which is another SPICE file. Oop, not the gate. And you find lambda by finding the y equals mx plus b curve fit around here. And that will ultimately give you how much the current is increasing with VDS. All right. And so I'm actually taking 2 points here and here and then finding the slope. All right. So I just extract 2 points and then calculate it, and that gives me my lambda. Now, lambda changes quite a bit with that gate voltage. In this case, the threshold voltage is around 0.7, and lambda is kind of large, and which happens, right? So that means your gain won't be as high. What I find is but those are sub-threshold effects. So actually I plotted out about a half a volt above threshold voltage. So I'm getting 625 micro. Now you might say, how do you know where to do it? Well, you've just extracted VTO in a previous step. So you kind of know where to be. But you could also do a CV curve on a transistor as well, and that could give you an estimate of VTO to know where you should be. So all of these have their NMOS counterparts, and you kind of end up taking absolute values of things just to get the code to work out. But that's pretty much it, except for the sub-threshold, or there's these other parameters that I don't know how to extract at this point. But these are the big ones, right? And the other ones can be estimated, or actually a more detailed analysis can be done in TCAD. But all the capacitances, would be a whole other extraction routine, and in fact you're just worried about the capacitance. You stop doing these DC sweeps. But that should help you figure everything out.